We can start.
Buongiorno,
We start.
Okay.
Yes. Okay, so welcome everybody, and today we start our workshop with the talk by Chiara Toldo. She's in Brussels, and she's going to tell us several things about black holes, quantum black holes probably, and okay. Please, you have 1 hour. Sorry for the delay.
No, don't worry. Okay. Okay, thank you so much. I hope you can all hear me very well. I'm very sorry to not be able to be there in person, but hopefully I will come there again next year. And so today I'm gonna tell you some of my work in progress on constructing some exotic, yeah, let me know if there is any interruption. Some work in progress about the construction of some exotic black objects, so black holes in 5D, such as black rings, black Saturns, and multi-center black holes. This is based on work in progress with Jay Armas and George Batzios, which are in Amsterdam, Alessandra Niecki in Padova, and Pedro Marto, which is in Utrecht. And it's also, towards the end, I will mention also some work in progress with Antonio Mariti and Riccardo Salto are at University of Milano. So let me just start now, if I allow me. Okay. So just a very generic introduction. So black holes indeed have like recently, well, have always been, but in particular recently become a cornerstone for contemporary theoretical physics. So indeed there are astrophysical observations, but also they connect, like they allow us to connect to quantum information, and they are a central object in holography. So indeed black holes have thermodynamic features. They are indeed ensembles with entropy and also they emit radiation, so they have like a Hawking temperature. And in particular, my interest in these objects for this talk stems from some recent development of microstate counting for ADS-CFT. So in particular, people managed to give a meaning of the entropy of ADS5 black holes, counting states in the dual field theory, that in this case is n equals 4 Superior Mills. And so for the single center black hole, this is a reason, like that's been successfully achieved. But in this talk, I'm gonna try to, let's say, or propose or try to argue that there are other configurations which are also very interesting in ADS5 or in 5 dimensions, which are not just the single center black holes, but they have some sort of exotic horizons. But so let me take a step back and tell you a bit what are the very generic features of black holes. So according to general relativity, a black hole is a simple object.
It's not scrolling the.
I think we don't see our screen.
We see just a fixed image.
We see just a
You
second.
don't have okay, let's see. Do you see it now?
Now we see.
Now we see something even stranger.
Oh, I have a toolbar. So you should exit the full screen and simply share that application.
Let me see. Okay, so I stop sharing, but then I share again, and let's see. Maybe I can share the desktop. So maybe if I share the desktop now, let's see.
Now we
Who's this?
different slide.
And then I'm gonna do
Change
this
slide.
full screen. Let's see if now you.
Yes, now it's better. But the change slide.
Okay,
great.
perfect.
Okay, because I don't know why. For me, it was showing before, but okay.
Okay.
So now you can see full screen and
No,
Yes. No hair.
no hair. Okay, yes, that's the slide. Okay, so I will go on now. Okay, so according to general relativity, just please interrupt me if there are any doubts or anything, any technical things that are not going well. So a black hole is indeed a simple object, is parameterized by mass, charge, and angular momentum. So under certain under let's say mild assumptions, classical Noether theorem holds. So it holds for stationary electrovacuum solution, in particular with the abelian gauge fields, in asymptotically flat space, in 4 space-time dimension, and for connected event horizons. So indeed, there are also solutions which are multiply center, but the Noether applies to each single components. So, and in general, the statement was that every stationary asymptotically flat connected horizon electrovacuum black hole is uniquely determined by mass, J, and Q. This is in 4 dimensions, asymptotically flat. However, in higher dimension, this is not true, because higher dimension, for instance, mass, angular momentum, and the charge, are not sufficient to uniquely characterize a black hole. So there are black holes with different topology of the event horizon. In particular, there are, for instance, black rings that were discovered first by Emparan and Real, and whose horizon topology is S1 times S2. And also black Saturn. So black Saturn is this object here. Like I hope you can see my pointer. Basically, it's like a black hole which is surrounded by a black ring. So the Y is a Saturn. And the rings are viewed heuristically as taking a black string, so a straight object, black string, bending into a circle and then making it fast enough in such a way that it stays open. That's the way how we heuristically view it. So these solutions are, let's say, well, exotic, but they are really there. They can also preserve supersymmetry, and they have been studied quite well. So so far, all the studies hint at the fact that indeed, when you go to higher dimension, higher than 4, you have a much richer solution landscape than in 4D. And what happens, for instance, for the thermodynamic phase space is that indeed let's say for angular momentum which are low enough, the configuration which dominates the ensemble is the single center black hole. But if you make this black hole spin fast enough, the horizon becomes kind of squashing and pancaking in such a way that for large enough angular momentum, the configuration which is the one which is entropically favored is indeed the black ring, which is something which is indeed extended. Moreover, there have been many different developments. For instance, black rings are amenable to microstate counting, and thin rings, also given that they are, let's say, made out of the string, they inherit Gregory-Laflamme instability. So they have many different curious features, but also they're also very interesting configurations. I cannot understand if there are any questions. So I don't know if I
don't have questions, but
okay, because I can hear some echoes maybe, but okay. So this is for what concerns asymptotically flat space. So the first studies for black rings were constructed in asymptotically flat space. But of course, it's very interesting to understand whether these objects, they are there also in anti-de Sitter space, because indeed these objects can have interesting an interesting effect for implications in the context of ADS-CFT, because they have different, for instance, there can be different phase transitions, they can be interpreted in terms of the conformal field theory. So ADS, as we know, acts like a box, so the gravitational potential might in principle interfere with the equilibrium conditions between centers. However, the black rings exist because of a balancing of the gravitational self-attraction and the centrifugal repulsion. So one might think that spinning a black hole fast enough should counterbalance the ADS potential. And this is indeed true. And these black rings in ADS were indeed constructed. And the first example was in a paper by Caldarelli, Emparan, and Maria Rodriguez, which might be in the audience. And they have been constructed via approximate methods. So basically, like in the probe approximation, basically thin black rings were constructed with this method here that I'm gonna explain later on in my talk. But so they have been proven to exist, and they exist with arbitrarily large radius. And these black holes, indeed, they spin comparatively faster with respect to the asymptotically flat space, because they have to counterbalance the pressure of ADS. And one can also find the black Saturn solutions. So in this talk, I'm gonna build up on this work and develop the black fold equation for solutions which are charged. So in particular, we will be able to construct charged black rings and also black Saturns, and find the equilibrium condition that will lead to new solutions in both Minkowski and ADS. And we will investigate also the possible supersymmetry, because if you find supersymmetric black Saturns, black rings, and so on, then they might play a role in the microstate counting in the dual CFT. So what is it known about supersymmetric black rings and black Saturns in anti-de Sitter? So this has been something which is there have been several studies, And so the first study was in the original paper. And in the original paper said that showed that indeed, if you take a supersymmetric black string and you try to bend it into a ring in ADS space, you cannot do that because the supersymmetric black string cannot provide the necessary pressure to counterbalance the ADS potential. So this is a particular kind of string that these people consider. There were also different studies by, for instance, Conduri, Lucetti, and Real, that indeed investigate the possible new horizon geometry in ADS5. So in this case, these people also, they didn't find possible new horizon geometry for the ring in minimal supergravity, but can be there if you add, for instance, scalar fields. So in pure ADS plus Maxwell plus Chern-Simons, they don't seem to be there, but you need, for instance, other vector multiplets. Quite recently, so these are studies which date back quite a number of years, decades, let's say. Quite recently, I said there are two groups. I'm sorry if I am forgetting some of the authors, but in general, so I'm quoting these two different recent work that indeed construct, well, actually compute the on-shell action via for BPS solutions via equivariant localization, and it seems that also there it is shown that at least under specific conditions, you cannot find a supersymmetric black ring in minimal 5D gauge supergravity. So these are three things that seem to hint at the fact that supersymmetric black rings in ADS, they are harder to construct or they can really not be there. In particular, the first study here, though, makes use of a particular configuration of a supersymmetric black string and show that it cannot provide the necessary pressure. Our approach instead will be to generalize this supersymmetric black string. So if you dig enough in the literature, you see that there is a supersymmetric black string that generalizes this configuration here, and it seems to evade some of this no-go theorem that arise here. And so what we're going to do is to show you how we construct these solutions, and then we are also in the process of studying the phase space, but this is still very much of a work in progress. So the results that I'm going to show you, they will be unfortunately a bit partial in this thing. And towards the end of the talk, I'm also going to introduce a different setup. So in this case, I'm also going to show you that there can be configurations for which, so you don't have a Saturn, so it means that you don't have a black hole and a ring outside it, but outside the black hole, you might have a point-like probe. So in general, so the probe analysis that I showed before can, in this case, we do this probe analysis in the full string theory uplift. And for this kind of second part of the talk, I will show you that indeed we can find solutions in which we can find supersymmetric bound states in which a black hole is in the center and a point-like object made by a wrapped D3 brane is on top of this and stays in equilibrium at a finite distance outside the horizon. So this is really like a composite object. We are going to work in the case of ADS5 black holes, solutions of particular truncations of Sasaki-Einstein manifolds. In particular, we're gonna focus on the conifold truncation, and by wrapping D3 branes inside internal dimensions of this particular manifold, we get a point-like particle in 5D. That indeed upon back reaction, it can become possibly a multiply center black holes in ADS5. So this is somehow a complementary picture with respect to what we had before. Instead of having a ring, we have a point particle. And we did this study by inspecting the DBI action. And towards the end, I will also tell you how our procedure and our analysis fits in the framework that was recently put forward by Miwala and collaborator, that indeed asserts that the endpoint of the superhelium instability will be solutions which are also composite. They're called gray galaxies and dressed black holes that are indeed like they're also made out of a central black hole and some cloud of probe branes. So I will also make contact to the gray galaxies. But so this is finally the outline of my talk. So in the first part, I will tell you how to construct black rings and black Saturns, possibly in ADS5. And towards the end, I will have 5 or 6 slides about this other framework that tells you how to construct, indeed, on ADS5, these bound states of wrapped branes. Okay, then I will go on first with the construction of charged black rings and Saturn. So I'm going to introduce now briefly the framework of black folds. So for the black fold approach, I'm sure if Maria is in the audience, she's an expert on this. And so in this approach, the key observation is that indeed in specific black hole objects, such as, for instance, thin black rings, you can have situations in which you have two very different length scales. In particular, you have that the black rings have a topology S1 times S2, and they are characterized by a radii R. We call R the radius of the S1, and R0 the radius of the S2. Moreover, if you, for a ring which lives in anti-de space, you have an additional ADS, like length, which is the ADS scale, like the inverse of the cosmological constant. So in general, what you have is that if this radius here is much smaller than either the curvature of the embedding or the curvature of the ring, the black hole really looks locally like a flat black string or like a flat black brane. And the black hole then provides an effective theory for describing setups where the deviation from the flat string occur on scales which are much longer than the brane thickness. So in general, it is a long wavelength effective approach that you get upon integrating out the short wavelength degrees of freedom. So the black hole in this case, the name comes from the fact that you have a black brane, in this case a black string, which is wrapped on a compact submanifold of spacetime. And so when this separation of scale holds, the gravitational problem can be approximated by an effective Wood volume theory, and the black hole equations of motion follow only from the conservation law, for instance, from the conservation of the stress energy tensor. So you trade solving the Einstein's equation by solving an easier problem, such as the conservation of the stress energy tensor. In this case, you are able to take to see whether a black string, which is boosted, can be actually closed off and bent into a black ring, into a circular shape then. So all of this, so the first step in all this is we consider in all these computations, basically we consider the string as a probe. So it is making a thin black ring entails taking a string, considering it as a probe, and then see whether the Wood volume theory allow you to basically find some equilibrium condition. So at large distance in the direction transverse to the string, then the gravitational field it creates is the same as an equivalent circular distribution of angular momentum. So finding the black hole, solving the black hole equation entails finding what is the stress energy tensor for your black string by going far away and treating the string as a point-like or a circular distribution of matter, and then imposing the conservation of the stress energy tensor, which in the case where you don't have charge, it looks like this. So this is just the covariant derivative of the stress energy tensor of the string is 0. And for a thin brane, this is equivalent to impose the so-called Carter equation, in which basically this equation here gets split into components which involve the extrinsic curvature of the embedding geometry. So the equation that we are going to solve is really this one in the box, where the thin brane, basically the string provides the stress energy tensor, which is this one, and the embedding geometry, so the space in which this solution lives, provides the component of the extrinsic curvature. So just as an example, what we're going to do is we're going to consider a neutral black string. So a neutral black string is obtained, for instance, by taking the Schwarzschild solution and adding an additional coordinate z that will be indeed the length of the string. And we're also going to perform a boost along the string direction z, which is really this one. So if you go the metric that you get, it's indeed it is transformed because you do a boost. But if you see it from far away, the stress energy tensor relative that sources this solution here, it's actually this one. You can easily compute it. You can just go far away. You can change a bit the coordinate, but if you see, it is something which is a circular, let's say, point-like distribution of matter, where indeed the boost parameter enter. And so what you're going to do is you want to see whether the conservation of this stress energy tensor is compatible in spacetime such as Minkowski or even in de Sitter. So you're going to take this string and put it in ADS space. ADS space has this metric here, global coordinate, and we decide to put the string or the ring at theta equals 0 and a specific radial coordinate r. And so you need to use them like proper like embedding coordinates, and so the t and the z are the coordinates on the worksheet of the string or of the ring, and then tau and psi are the ones of the embedding spacetime. So if you insert everything into the Carter equation, this is the condition that you get. This is the one on the left. So it's a condition on tt and tzz. So if you put inside these values here into the Carter equation, you manage to find a relation between the boost parameter and the equilibrium radius. So this means that this solution here, this equation here can have solutions, and it means that indeed, like this particular neutral black string can be there unperturbed, let's say, can be there in equilibrium in asymptotically ADS space. And what it was found also was found that indeed the radius of equilibrium depends on the boost parameter. So you can take this neutral black string and bend it and put it in ADS. This was the first example found by, indeed, by Caldarelli and Paran and Rodriguez. So in the same paper, they also constructed Black Saturn. So instead of putting here only ADS space, you can also decide to put the metric of a black hole in ADS, for instance, and then you can construct a Black Saturn in ADS space, still by bending this neutral black string. In the same paper, it was investigated also whether you can bend a supersymmetric black string, same in ADS, but a different kind of background geometry, a different kind of probe geometry, which is the supersymmetric black string. And so the supersymmetric black string that they have considered is the string that was found by Bena in 2004, and it has this metric here. It is also supported by a gauge field. Most interestingly, if you compute the stress energy tensor for this supersymmetric black string here, you see that it has two components, but it lacks a third component. In particular, it lacks the component TZZ. So if you try to plug this into the equilibrium condition here, you will see that since TT is non-zero, this cannot be satisfied because you have 0 on this side here. So this solution, this means that it was also still found in the same paper, that it seems that there should be, like there cannot be any black ring formed by bending this supersymmetric black string in ADS5. And this will have indeed consequence. So it means that supersymmetric black ring, by bending this string, cannot be there. And I give you a bit of a spoiler alert. What we find is that by generalizing this string here, it seems that the ring is possible. Actually, supersymmetric black ring is possible. Also, in order to generalize these solutions, what we need to do and to find, for instance, charged black Saturns, and because so far we have put the string in backgrounds which are not really charged. What we consider first a more general string probe that I was anticipating before, but also we are going to consider the fact that the Carter equation gets modified once we couple it to charged background. So if you want to put a charged string on a background of a charged black hole, you have also to, like the right-hand side of the Carter equation gets modified. And it contains, for instance, the 1 and 2 form current that are relative to the probe string. So the equilibrium condition is a bit more involved than this one that I showed you before, which is very simple. But nevertheless, we can find it in a closed form. So first of all, I'm going to show you, like I'm going to tell you how to couple it to charged solutions. So, and then I'm going to tell you how to generalize the string. So first of all, coupling to charged solutions. So we work in theories of 5D n equals 2 supergravity, can be gauged or not gauged. It depends. If you have a gauge supergravity, you can have anti-de Sitter solutions. And in this case, these are parameterized by this cosmological constant. If you set the gauge coupling to 0, then in general, you can have ungaged supergravity, so it allows for Minkowski, asymptotically Minkowski configurations. But okay, so minimal n equals 2 5D gauge supergravity is Einstein-Maxwell with a Chern-Simons coupling. And so if you compute the equations of motion of the gauge field plus the Bianchi equation, you get this particular equation here. What you want to do now is to allow a source, like a string acting as a source. So you couple this particular system to a probe brain with an electric one-form current and Matkal J1, it is a magnetic two-form current. And so the Bianchi identity and the equations of motion lead to the following conservation equation for the two currents. They are derived actually from this paper here that I mentioned here. In this paper, there is also, like, they study the higher group symmetry actually of gauge supergravity. I'm not really familiar with this, but for our purposes, we need these two equations to find out the final form of the stress energy tensor coupling. And so indeed, once you find these relations here, you get that the right-hand side of the Carter equation becomes this. So indeed, we found now the way actually the gauge field and the currents of the string coupled to the background. So on the right-hand side, you have the Carter equation that I showed you before, sorry, on the left-hand side. And on the right-hand side, you have the coupling of the current where F is a three-form that indeed I didn't show you here, but in general, it can also be, it's defined as some sort of like a dual of F mu. And this also comes, like this whole formalism that was developed in these two papers also comes with a different definition of conserved charges. So once you allow for this particular additional one-form current and two-form current, the definition of the charges also changes accordingly. It was found by this paper, but it's something, that definition that you can use it, and you can just use it and compute your charges of the Saturn and of the ring. So this is the first part. We have first modified our Carter equation to allow for couplings to these currents. And then the second generalization that we are adopting is that we are gonna take a more general black string solution that was found by Compare, Debil, Stotin, and Amitabh Virmani. So this is again a solution of 5D minimal gauge supergravity. So the metric is a bit complicated here, doesn't really probably tell you a lot, but in general it has many, it is a string which has indeed a charge, electric and magnetic charge, and it contains indeed many work factors and many parameters. In total, it contains 4 parameters because it has the mass, the electric and the magnetic charge, and also the boost parameter. So I just fleshed out the solution just to say that it is there. It is a solution that was found via some solution generating techniques of supergravity. And you have to dig in a lot of papers supergravity to find this. This is the most general black string solution which is known in this sort of theory, and is more general than the one that the initial paper dealt with. So it is indeed parameterized by four numbers: mass, electromagnetic charge, and the boost parameter, which is this parameter gamma, which indeed provides the angular momentum for the string. And so given the string, again, by going far away, you can compute what is the stress energy tensor and the current that will be compatible with the black string metric, and this becomes this two boxed equation. So this parameter TAB and J1, and also Matkal J2, that will also be there. I didn't show it here because it will not play a role for our backgrounds. But these quantities here need to be inserted then in the Carter equation to find the equilibrium condition. So the picture is this. Basically, we have this generalized equilibrium condition. We are going to choose the black hole background that we like. It can be, for instance, both in asymptotically flat or in ADS. And it has it is supported by its own gauge field, F mu nu. And then on top of that, we are going to take the generalized black string solution, which has T mu nu and J mu, as I showed you here. And then we're going to plug it into the Carter equation. What we're after is this R eq. We will see whether there exists an equilibrium distance, which is positive, for which the string can stay outside the black hole. In this case, then we will be able to find, so if our equilibrium is positive, then it means that we are able to find black Saturn. So we first are tackling, so this is still again work in progress. So what we are tackling now is the Minkowski case. So we are going to take a black hole, which is the electrically charged black holes with two angular momentum of equal magnitude. which is the Cvetich-Hume solution, and which has the supersymmetric limit, which is the BMPV black hole. So it's a black hole from a solution of supergravity with charge, which has a supersymmetric limit, and we are going to try to put on top of this the general black string. We also adopt a simplification. Of course, if you have in order for your black Saturn, sorry for going back and forth, but in order for your black Saturn to be in equilibrium with the string, you also need to impose that the temperature of the black hole in the center is the same as the temperature of the string. Otherwise, you don't have a configuration in full thermodynamic equilibrium. And as a first case, we are also imposing supersymmetry, meaning we are imposing that we are working with the BMPV black hole here and with the supersymmetric black string here. So the limit of the 4-parameter black string of compare and collaborators, the supersymmetric limit, is characterized by 3 independent parameters. It can be written quite compactly in this form here. So it is parameterized by this parameter delta Q big and Q small. These are the 3 parameters of the string. And you can also compute the stress energy tensor in this particular supersymmetric limit. It has this very nice form here. So it is a very compact form. But in particular, you see that TZZ is non-zero. While before, for a supersymmetric black string that was used in the original paper, TZZ was 0. And this solution here reduces to the 2-parameter black string for delta equals to Q. So for delta equals to Q, indeed, we retrieve TZZ 0 as we had before. But it's a more general configuration which preserves supersymmetry, which has non-zero pressure here. So it will have consequences for the equilibrium condition. So this is the stress energy tensor for the string. We also computed its current. And so we are ready to plug it into the Carter equation. So the Carter equation becomes a bit gigantic because you have to compute the extrinsic curvature of the BMPV black hole. It's a bit, they have a bit of big expressions, let's say. But nevertheless, you can try to solve it for an equilibrium radius, R equilibrium. So it's, of course, it becomes a polynomial of 8 order, if I'm not mistaken. But so you cannot find the form like in an analytic form, but you can plot the result with Mathematica. And so what we have verified now is that if you further set delta equals to Q, the solution reduces to the 2-parameter string on the BMPV. And this solution we already found analytically by Gauntlet and Gutowski. So this is just a sanity check that we performed on our computation. And then we're going to see whether with the 3-parameter string, by playing around with all the 3 parameters, you can actually get something new. So first of all, what we noticed at first is that the fact that the string with 3 parameters has a non-trivial TZZ means that there do not exist supersymmetry black ring with this string in asymptotically flat. Why? Because in asymptotically flat, you have to take mu equals 0 to have Minkowski. And so all these terms go to 0. The first term goes to 0, second as well, and also the right-hand side. You will need to balance this term here, but you cannot. So it means that in asymptotically flat, this generalized black string has too much pressure. It will not be able to actually be bent into a ring in asymptotically flat. But if you consider the Saturn, meaning if there is a black hole with the non-vanishing parameter mu and so on, in principle, you will be able to find a solution to this horrible equation. And this will provide a new extremal black Saturn, which most likely will not be supersymmetric because the ring itself, we've seen in the previous bullet point that it will not be supersymmetric.
Sorry, how many real roots should have this equation?
I think that in general they should have, if I'm not mistaken, something like 8 roots, but this is still very much of a work in progress because we also are doing, it should not have 8 real roots, let's say. Maybe some roots are complex or so on and so forth, but we are still studying this equation here. It's still very much of a work in progress. We just performed some sanity checks for this first point.
Build the solutions in new already.
Yes. So there are some analytic solutions. So the paper by Gauntlet and Gutowski provide analytic solutions for concentric black ring and supersymmetric concentric black rings and supersymmetric black Saturns with the 2-parameter string. And so we managed to show that we can retrieve in the probe approximation their solutions. But now we are putting the full parameter space that we have for our generalized black string, and we are trying to study whether there exist solutions for this equation here. So it's still very much work in progress. I cannot be very more explicit, unfortunately, at this moment. But the fact that the string expression will have a consequence that I'm going to come in a few slides. Yeah, you let me know if you have other questions. I'm always happy to answer. Okay, what I was saying. Okay, we are checking now whether there exist solutions to this equation here. It will be new extremal black Saturns. And we can also provide plots for very generic black Saturn with temperature. This is again very preliminary, so take it with a grain of salt. But this is something that so this is the black hole solution, so the Cvetich-Hume solution, and this will be the onset of the general the ring, and at some point there is also I think the Saturn on one of these curves here. This is a Pedro produced this just a few days ago, but it's still very much of a work in progress. But this is the graph that would resemble the graph that I showed you in one of the previous slides, in which the black holes are the favored solution for low angular momentum, and for high angular momentum, the rings and the Saturn are the one dominating. But so before finishing up this section, I just want to point out something that so that is very nice about this, or very curious, let's say, about the string. So this generalized string that was found by these people, I mentioned it has this particular form for the stress energy tensor. So in particular, it has this component here that was 0 before. So before, if you remember, the fact that the supersymmetric 2-parameter black string had t equals 0 was the obstruction to find a supersymmetric black ring in ADS5. Because indeed, in that case, TZZ was 0, and there was no way to balance this equation for ADS space, where this term here is 0. However, in this case, now we find that generalized black string in which this component is non-zero. So if you plug it into this equation, actually, you find that for ADS5, the warp factor V of R is this thing, and then you actually have a solution which can be positive for the equilibrium radius. So as I was mentioned before, in Minkowski, you cannot do this because this is unbalanced, but in ADS5, it looks like you can balance actually this equation here, and you can find a solution for the equilibrium radius. And just to be completely fair, there was an observation of this paper already in 2009 that points out this. They don't compute the equilibrium radius, but they point out the fact that given that this string has this term in green here, one could actually find supersymmetric black rings in ADS5, at least naively. What we did is like a one-line computation and check that actually this is the equilibrium radius, and it seemed to have the chance to be positive. So it seems to be a well-defined thing. So it just looks like we have a string that is supersymmetric and can be bent. They can provide that has the necessary pressure to counterbalance the ADS potential. So in principle, it would provide a black ring in ADS5. However, one needs to check, well, it is not guaranteed that, that bending the string will still allow to preserve supersymmetry. And we have just studied at first, well, let's give it a bit of an overview on the various kind of killing spinner that are present in gauge supergravity. And it seems that the string somehow we cannot really find, at least for now, a suitable killing spinner among the ones that are known for this string to be supersymmetric in ADS space. So this string has magnetic charge, so it has hope to be supersymmetry because in anti-de Sitter, supersymmetry can be preserved via the topological twist, which requires magnetic charge. but it's still something that we need to study because we don't seem to find a killing spinor which is compatible with this 2B ring. But nevertheless, it is something very interesting because it seemed to be a counterexample of what people, I mean, it challenged the general lore about non-existence of Aries 5 black rings. It could be indeed that bending the black string will break supersymmetry. This is something that we need to study. And what we need to study is also to check whether indeed Saturns are possible by studying this horrible equation that I showed you before. So all of this is to be continued, but I hope that this is a bit of an appetizer of why these things are actually kind of nice and exciting. So I have in the last maybe 10 minutes then, so this is, I wrapped up in this case, what happens when you have this charged black ring.
Does she hear me or do I need to?
Yes, maybe, yes, I think, yes.
So what are you comparing in that plot? Like what is rotating
I don't know. I mean, what is in which plot? Sorry.
in the entropy plot?
Okay. The entropy plot is it's super preliminary, so it will be.
That's Myers-Berry. Then the Saturn, what is rotating there?
I think that so the Saturn. Sorry, I think for these ones we still have. I think this would be a non-extremal black string on a non-extremal, Myers-Berry black hole.
Okay, because but what is charged in your Saturn?
In my Saturn, the string has electric and magnetic charge, and also sorry, it's not a Myers-Berry, it's a Svetich-Hume Saturn. So it's a Svetich-Hume background black hole, which is the non-extremal generalization of BMPV. So it's an electrically charged rotating black hole.
But it's not rotating the black hole.
The black hole, yes, it is. It's a BMPV black hole.
In 5 dimensions, rotating,
yes.
Charged.
Yes.
Okay.
It's like the BMPV, right? It's like a thermal generalization of the BMPV.
Well, maybe I don't. Do you have other fields in it?
No, there are solutions of minimal supergravity.
Okay, I see. But here the J that you have corresponds to both the sum of the rotation of the. You see, you have 2 objects now.
Yes.
What is J for you?
Yes, this is something that I think. I think it would be. Because sorry, I have to admit that this plot was produced very recently by my collaborator, and so I'm not really aware of whether J is the sum of the two or if it's just well, for sure for the black hole it's just the J of the black hole.
Yeah.
I will need to ask my collaborator the details of this plot. I'm assuming that it's the sum of the angular momentum of the both the black hole and the black ring, but I'm not really that sure.
Okay.
Yeah, I'm sorry. I can provide you more details once it was very recent.
Spinning and was thanks. Sorry.
No, of course. Yeah, so this is very preliminary, but it's let's say that this last thing related to this is just a one-line computation. So this is something that indeed it's very curious, the fact that we seem to find some equilibrium condition given this generalized black string. If you have further observations, Maria, we will be very happy to listen. But okay, so in the last 10 minutes, maybe I'm gonna briefly mention some work on wrapped brains on T11. This is with a master student, Riccardo Salto, and with Antonio Mariti. So in this case, what we wanted to let's say our setup was let's say a setup that mimics let's say some construction that was done for 4D black holes of Frederick and collaborators. in which basically they were trying to understand whether multi-center black holes were possible in anti-de Sitter space, in ADS4. So this, they looked at the 4D black hole scenario. And so their setup was a setup in which you have a background black hole of a very big mass and a small black hole, let's say, made out of wrapped D brains of negligible mass. So this basically this black hole can be considered a probe with respect to the big black hole in the center. And they were seeing whether from the DBA action one could find actually bound states between the wrapped brains outside the black hole and the black hole itself. So in this case, upon including back reaction, these actually could be multi-center black holes in ADS4. So in general, was what we wanted to like our initial idea is to let's say adapt this framework to 5 dimensions by indeed checking whether bound states of black holes, in particular black holes which are supersymmetric, are possible, because this might have relevance for microstate counting. You might have a configuration which is supersymmetric, which instead of having one center, might have two centers. And so they might play a role in the microstate counting, especially if supersymmetry is preserved. However, these solutions were not found in the literature. They were not found so far. And it's very hard to indeed to solve the Einstein's equation analytically or numerically. So you need to solve PDEs for multicenter black holes. So this is not quite a very approachable problem. So we decide to resort again, like these people did, to the probe approximation. So we take a black hole in the center, which is an ADS5 black holes, can be supersymmetric or not. We choose to work in a supergravity truncation, which is the universal truncation, so it can uplift on different kind of Sasaki-Einstein manifold. And we choose as a Sasaki-Einstein manifold the conifold, which indeed is a manifold which has a particular topology that includes non-contractible cycle. So indeed, this brain can wrap this non-contractible cycle, and they are stabilized then by topology, so they cannot shrink their volume to 0. While, for instance, the giant gravitons instead are stabilized by angular momentum, these brains will be stabilized by topology. So wrapping these 3 brains on internal dimensions of your manifold makes them appear as point-like in 5D. So in your ADS spacetime, you'll have a black hole and a very small point-like probe that upon back reaction can become a different black hole center. So the entire configuration can become, in principle, at least a multi-center black holes in 5D. I put it here on a footnote because I didn't know how to actually put it. I don't know if in the audience there will be some of the co-authors that even like a group at CISA also studied the DBI action of D3 brains on ADS5 black holes. However, there are probes in Euclidean geometry and their brain placement is a bit different than what we have. So we do not have any points in common with them, but I would just wanted to point out that people also have performed this sort of studies of probe brains for different kind of reasons. But okay, so our setup is that we are gonna, so the background black hole will be an ADS black hole, supersymmetric black hole, which is the Gutowski-Real black hole. So it has let's say, the anti-Sitter generalization of the solution that I showed you before, the Cvetich-Yung solutions. So there are ADS5 black holes with charge, like with this electric charge, and 2 angular momentum of equal magnitude. And we are also going to consider their thermal generalization, the so-called CCLP solutions. Again, so there are 5-dimensional black holes which are characterized by this sort of metric with these work factors. They are parameterized by 3 parameters that coincide, then they can be rephrased in terms of mass, charge, electric charge, and angular momentum. Sorry, I'm just gonna drink some. So this will be our background black hole. It's an ADS5 black hole that has a supersymmetric limit. And also we work in gauge supergravity, in minimal gauge supergravity, which is a so-called universal truncation. So it means a solution of this theory can be uplifted to type 2B on, as I was saying, different Sasaki-Einstein manifold. And for our purposes, we choose the conifold, the T11 manifold, which has topology of an S1 fibered on 2 S2. and it has non-contractible cycles. And in general, so the ES5 correspond to this, the black hole metric. And this is the 5-dimensional manifold in which I single out the two spheres. And psi is the fiber coordinate, and notice that the gauge field appears also here. So it's non-trivial. It appears in this factor here. Also, there is a 5 form that, of course, is known in the literature. I think actually I forgot the citation here. It's a paper by Cassani and Faido, but it is something that is well known. So on top of this black hole, which can be uplifted on T11, we're going to put some wrap D3 branes. And so we're going to consider the dBi action with the volume term and the West-Subino term. And we choose this following embedding, which we borrowed from Ericsson, Hoyos, and Jokela. And so it means that this the brane embedding is such that the brane is wrapping basically an S3 inside the T11. It's parameterized by parameters indeed tau, which is the time coordinate, zeta, beta, and gamma. So after you do all the procedure, you can extract the effective potential from the dBi action. And you also assume the fact that the probe actually rotates in the space-time direction. So it has a non-trivial p psi. And you get this sort of potential here that you can plot for many different configurations. So what is salient about this thing is that if you impose supersymmetry of the background and this particular embedding, you can show that actually kappa symmetry is verified. So this embedding is supersymmetric. And for once you have the black hole background, which is also supersymmetric, you've managed to find a marginally stable BPS minimum. So it means that you have actually a minimum of the potential, which is at 0. So this is the minimum that arrives at the black hole horizon. And then there is another minimum at the same height, at 0, outside the event horizon. So that's why we call it a marginally stable BPS minimum, in which basically the probe can actually stay here at this distance outside the horizon. So it's a BPS, it's a BPS bound state. And so first of all, let me mention, it appears at the onset of angular momentum superradiance. So indeed, there is a particular value of omega for which this minimum appear. And this minimum is also, if you take the flat limit, is not really there. The minimum gets washed away. And this is compatible with the fact that in asymptotically flat space, there do not exist any multi-BMPV solution. This was from a work of a PhD student of Harvey Real. And so this situation is somehow similar in spirit to what happens with the gray galaxies. So in general, so Miwalla and their collaborators indeed point out, have a series of studies in the past, let's say 3 or 4 years, in ADS5 times S5, where indeed they consider these gray galaxies are objects which are a non-interactive mix of a black hole plus a disk of thermal gravitons. These are non-supersymmetric configurations, and this should be the endpoint of the angular momentum superradiance for the Kerr anti-de Sitter solution. So our let's say the results that we have in this case, they are very much similar in spirit. It seems that whenever omega is in the angular momentum superradiance interval, let's say the system prefers to be in a phase that is composed by a black hole plus an object outside the black hole. And indeed, this is from the fact that indeed angular momentum can be stored in other charges which are outside the horizon, and it seems to be the black hole does this more efficiently. So this is let's say the favored configuration. This is so the studies of Miwalla are mostly for Kerr ADS, so they don't involve the gray galaxies one. Are really for non-supersymmetric configuration. It seems that here we find this similar, like the same, the corresponding phenomena, but for solutions with the supersymmetry, at least in this conifold setup. Miwalla and together with Seo Kim and also other collaborations, sorry, it's a paper with 7 authors, they also consider supersymmetric configuration, but they consider in this case different kind of configurations on ADS5 times S5 they call them on top, on top of having ray galaxies, you also have other configurations which are called dual dressed black holes, in which a black hole, supersymmetric black hole, is also surrounded by a cloud of dual giant gravitons, which are the three brains which wrap an S3 inside the ADS5. So in this case, they don't wrap an S3 inside the internal manifold, but this probe wrap an S3 inside the spacetime where the black hole lives. So they are in some way, I want to call them spacetime filling brains. So we also verified that we actually have also this configuration here, the dual dressed black holes. We also have it in our conifold truncation. So we adopted this particular embedding for the D3, and also we find supersymmetric minima. And these supersymmetric minima arise, in this case, at the onset of charge superradiance, not angular momentum superradiance, but of charge superradiance. And this is pretty much exactly the same picture as Choi, Jain, Kim, Krishnali, and Miwala and Patel had for black holes in ADS5 times S5. So for charge superradiance, we have pretty much the same picture, the same instability towards emitting dual giant gravitons, while for angular momentum superradiance, given the fact that we are in the supersymmetric setting, we find the instability towards emitting the wrapped brains. So it seems that this picture is like this. We have these two channels for the decay of our black holes. So I come now. So these are also very preliminary results. The interpretation is still ongoing, but this is something that at least this is the results that we have so far. It seems that we verified kappa symmetry. So these are bound states which are supersymmetric. So okay, I come now to the conclusions then. So first of all, this talk shows that indeed the phase space of gravity in 5 dimensions, in particular in ADS5, is generically populated by composite objects. So they're not just isolated black holes, but actually you can put probe objects on top of black holes, and they seem to be stable. And via black folds or via the DBI action, we have provided a framework to compute the equilibrium conditions. And of course, we are in the probe approximation. So we are always not dealing with back-reacted object with exact solutions of the Einstein's equation, but indeed we are in the extreme mass ratio, in which one object is much smaller than the background black hole. So this, of course, gives insight about, again, nature of gravity, nature of topology of the event horizon. It also tells us where to look for back-reacted solution. Maybe someone that has a very powerful code for solving PDE can actually find the solutions exactly. And in general, it helps understanding which are the regions where the black hole solution, naive black hole, is subdominant. And one might ask, finally, I guess for me, the $1 million question, whether actually there is some evidence for all these composite objects for microstate counting. And so is there a room that people, for these exotic solutions from the computations of the superconformal index, so on and so forth? Well, the status for the superconformal index in T1 in the Klebanov-Witten, which is the field theory dual to the conifold truncation, is not very advanced. There was some paper by Francesco Benini and a group at SISA, but they compute the superconformal index in the larger limit, but they don't seem to find other saddle point corresponding to bound states, but time is not ripe. There could be that they focused only on one solutions. There can be other saddle point that contribute. I think that this point deserve a bit more investigation. So, and we hope that people on the dual field theory will help us in understanding what is going on. Okay, that's all what I wanted to say. Thank you.
Okay, so questions?
Sorry, probably I missed this. So, do you hear the questions or not?
I hear, yes.
Probably I have this. Other solutions was a string instead of a black hole inside this black saturn, or not?
No, sorry, I didn't understand. What can you tell again? Because I think I didn't understand.
So, is it possible to pass a string through this black ring and stabilize such a system, or not?
Is it possible to?
To place a string inside the ring.
To put a string inside the ring.
Yes.
Okay, you mean like well, solutions of this kind where a string is in between two black holes arise in the context of a C matrix, for instance, where basically you have a cosmic string between horizons of two black holes. So, and in general correspond to solutions which are accelerating. So it could be that, could be that it's possible, though you have to allow for a string. In this case, it's more like a cosmic string. So it's some sort of in the examples that I know, these things are singular solutions, but
Oh, I meant black string, like the same as used as a ring, but infinitely long and inside the ring.
infinitely long. So you mean connecting the ring with the black hole, or what?
No, it simply passes through this ring.
Okay. That I don't know. I mean, I think we will need to, we'll need to understand that. So far, we just work with with the solutions in which, you bend the string, but you consider only one string, the string that makes up the ring. We don't consider any additional object on top of that, let's say.
Okay.
I hope
Another, please.
it's clear how realize these objects in n = 4 supergiant mills are as operator is just the case of the Hoffman-Mallasena giant magnons, or it's not clear, it's an open question.
It's an open question for us, for sure. For some other people, that might be something which is a bit more clear. So we are still we're still very much into the initial phase of this work. We don't have a full picture, so I would not be able to. So for sure, these brains here, they are some sort of like, I mean, the Klebanov-Witten one, like given the fact that like it has some sort of like baryonic operators, like these are wrapped brains on non-contractible cycles, but I'm not really sure about the dual interpretation of this entire setup. We will need to it's something that we are thinking about in the moment, but we are not really that sure.
You don't have an answer, or
we don't have a full answer of what this, at least from where the status is now. We hope to have it by when we actually write up the paper. We don't know what is the good picture. We know what is the field theory dual, which is the Klebanov-Witten theory of this conifold truncation, but we don't know what these possibly multi-center black holes would be in the dual, what would correspond to in the dual field theory. At the moment, not. We hope to brainstorm at least some idea and try to come up with some interpretation. So far, the work has been only done in gravity, the gravity side.
thanks.
Okay, I've got more questions. I don't see other questions. So let's thank Chiara again. And we reconvene 11:40 for the next talk. Now there is a coffee break.
Ciao Chiara, grazie.
Ciao, ciao. Ci vediamo la prossima volta. Come sta andando?
Sì, certo,
Come sta andando?
bene, bene,
Ciao.
sì, sì.
Avete fatto il bagno anche?
Hai voglia,
Eh,
sì, sì.
molto bello, guarda.
No, molto male che tu non
Infatti,
non venire, mi
infatti.
dispiace.
Fa caldo lì, sì che fa caldo, no? Cioè,
Sì,
Sì,
qua
fa
fa caldo.
caldo,
Fa
si sta
caldo,
bene,
c'è
si
un
fa il
ottimo mare.
bagno.
Vabbè.
Vabbè, ma
Vabbè,
tu
vieni in un altro
vieni in un
momento,
altro
dai.
momento, hai un invito aperto.
Quando vuoi venire,
Quando vuoi
Rolling.
ce lo dici.
D'estate magari, che così posso
Vengo
fare il
da
bagno.
Questa data.
Esatto, e noi ci organizziamo.
Capito?
Bene.
No,
Va
no,
bene.
assolutamente.
Grazie mille. Grazie, ciao.
Ciao,
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 Ciao.
ciao.
a presto. Vabbè.
End.
Thank you. I'm sorry.
E-